Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and this is part 2 of integration by parts. In the previous video, I talked about how we could derive the formula that we use for integration by parts. We resort to using integration by parts when our other patterns of integration do not work. And I went through some examples. I'd like to show you more examples where you might have to integrate by parts more than once. Let's take a look. In my first example, I have the integral of x squared e to the x dx. I don't have any patterns that would allow me to integrate this. I have an x squared factor that's not part of the du factor. I have an e to the x factor. It's not part of the du factor for the other function. So this is where I'm going to use integration by parts. I have x squared written first, but that's not what you use to decide what the u will be. These factors could be written in any order. The thing that will determine what you choose for u should be what function becomes easier when you differentiate. X squared, when you differentiate, becomes 2x. E to the x, when you differentiate, becomes e to the x. So this gets simpler when you differentiate, this doesn't. So I'm going to choose x squared as my u. And I'm going to let e to the x dx be the dv factor. I need to know du, so I differentiate. So this will, du factor will be 2x dx. You've got to have dx's on your du and your dv factors. They're differential, so you need the dx. V will be the integral of this. So the integral of e to the x dx, it follows my exponential form, so it's just e to the x. Now I plug into my formula. U, which is x squared, times v, which is e to the x, minus the integral of v, which is e to the x, du, which is 2x dx. When I clean this up, I'll have x squared, e to the x, minus, pull the 2 out, and I have e to the x, x dx. So now I look at this integral. Am I able to integrate it using the patterns I already have for integration? No. Because I have this x, this factor of x that's not part of the du factor. This isn't part of the du factor either. So I'm going to have to do integration by parts again. Sometimes people will choose u incorrectly. I'm just going to show you quickly what will happen if you do that. If I let u equal e to the x here, and dv be x dx, this will be e to the x dx, and this will be 1/2 x squared. Notice that got more complicated. So then if you were to plug these values into your integration by parts to integrate this, you would end up with a more complicated integral again, with an x squared and an e to the x. So if you choose incorrectly, you will run into a problem. You're going to end up not being able to integrate. You're going to go, well, I'm back where I was. So that all that means is that you've chose incorrectly. Just change it. So I'm going to let u be the x, and dv will be e to the x dx. If you want, you can write the x first. So you can see that that's the u. Now we find the du factor, which is just dx. Again, v will be the integral of this, my exponential pattern of integration. So it's just e to the x. Now I plug this into my integration by parts formula to integrate this term right here. So I've got x squared e to the x minus 2. Let's remember that we're multiplying 2 to both terms that we get when we do integration by parts. So it will be u, which is x, times v, which is e to the x, minus the integral of v, which is e to the x, times du, which is dx. You can distribute that 2. Negative and a negative becomes positive. Now we have an integral that is simpler, and it's actually possible to integrate this using the previous patterns we've taken for integration. Again, exponential form. So this will be equal to x squared e to the x minus 2x e to the x plus 2 times this integral is e to the x. Once we've gotten rid of all of our integral signs at the very end, now we can put our constant of integration. Let's try a couple more. In our next example, we have the integral of x cubed e to the x squared dx. You might think that we're going to have to do integration by parts 3 times, but this is an example where you might have to do a little bit of manipulation with your factors. So if we were to say that this is our u and this is our dv factor, before I find du, what I want to take a look at is what will be the integral of e to the x squared dx. In order to use my exponential form of integration, I need a 2x here. The 2 I can play around with, but the x I can't. So I can't integrate that. However, I could grab an x from here. I could write x cubed as x squared times x. Then this will be my u, and this will be my dv factor, because I know I need an x here. So let's rethink this. So therefore, u is now x squared, and dv will be e to the x squared x dx. To find du, we differentiate, so that would be 2x dx. To find v, we integrate. This is our exponential form of integration. We can fit into that pattern. The derivative of x squared is 2x, so I need a 2 here, which is fine. I can introduce a 2 as long as I balance it. Now I can integrate this. This integral will be 1/2 e to the x squared. So that's the v. Now that I have my table complete, I can plug everything into my formula. So my integral will equal u, which is x squared, times v, which is 1/2 e to the x squared, minus the integral of v, which is 1/2 e to the x squared, times du, which is 2x dx. I'll just clean it up a little bit. 1/2 x squared e to the x squared minus. Now I could combine that 1/2 and that 2. However, I know from this that I need that 2 as part of my differential. So I'm going to just move the 1/2 out and leave this as e to the x squared 2x dx. I already know how to integrate this. I did it. So this will equal 1/2 x squared e to the x squared minus 1/2 e to the x squared. Now I can put my constant of integration. And I'm done. Let's try one last example. This example is a unique type, and you might encounter something similar, so I want to show you how you would deal with this. We have 2 functions, an exponential function, a trig function. Neither is the derivative or the differential of the other, so we cannot use any of our previous patterns. So we're going to use integration by parts. We're going to take a look at which function becomes easier when you differentiate it. E to the 2x becomes 2e to the 2x, so it doesn't really change. Cos of x becomes negative sine of x. It doesn't really change. So in this case, you could choose either of these to be the u. I'm going to choose e to the 2x as my u, which means cos x dx will be the dv factor. The derivative of this will be 2 times e to the 2x, and it's a differential, so I need my dx. And v will be the integral of cos of x dx. That's one of our basic trig patterns, so that integral will just be sine of x. So now I'm going to plug into my formula, and I'm just going to write this as e to the 2x cos x dx equals, and you'll see why shortly. So it'll be u, which is e to the 2x, v, which is sine x, minus the integral of v, which is sine x, times du, which is 2 e to the 2x dx. When I clean this up, I'm going to have 2, and I'll pull it out front of the integral sign, and I'm going to write e to the 2x first and sine x dx. This doesn't look any easier than what I started with. However, I'm going to do integration by parts again, and I'm going to let u be e to the 2x again. This time, sine x dx will be my dv. So v will be the integral of sine of x dx. That's one of my basic trig integral patterns. So the integral of that will be negative cos of x. So I'm going to plug these values in to my integration by parts formula for that. Remember, the 2 gets multiplied by each term. So u times v, so it will be negative e to the 2x cos x, minus the integral of v, which is negative cos x, times du, which is 2e to the 2x dx. When I distribute this 2 and deal with all of the negatives, I will get e to the 2x sine x plus e to the 2x cos x minus that 2 and that 2 would be 4 times the integral of e to the 2x cos x dx. Now you might be thinking, Laurel, we're right back where we started. And I would say, yes, we are. However, there is something that we can do to actually finish this question without doing integration by parts again. Because obviously if we do integration by parts again, we can just keep doing it and we're just going to keep going around and around and around. I have an equation here, and this integral is the same as this integral. So if I could combine those on one side of the equation, then I can solve for my integral. Let me show you. I'm going to add 4 times this integral to both sides. I have 1 times that integral on this side, so when I add 4, I'm going to end up with 5 times this integral. Now all I have to do to find what this integral is just divide everything by 5. So this integral will equal 1/5 e to the 2x sine x plus 2/5 e to the 2x times cos x. And now that I'm done, I don't want to forget constant of integration. So that's how we would tackle a question like that. Practice integration by parts. Set up a chart. I know it takes a little bit more time, but it will keep you in line. And if you find that your integral gets more and more complicated, then try choosing your u and your dv differently. The next video is going to be integration by trigonometric substitution, so one more method. Practice this, and when you're ready, I'll see you then. Take care.